In today's video, we are going to be looking at limit laws. We begin by looking at two basic limits. So if we look at this graph right here, this is the graph of the identity function f of x is equal to x. Now, no matter what value we're approaching, so let's say we want to approach the value 2. So we want to approach, let's say, right here. What is f approaching? Well, it appears to be approaching 2. Now, if we want to do 4, what value does that appear to be approaching? Oh, it's approaching 4. So it is easy to see then that the limit as x approaches a of just x will be a. Here we have the constant function f of x, and for this graph it's f of x equals 2. Now notice that no matter what a we want to approach, let's say we want to approach negative 2, f will be approaching 2. We want to approach 2, f is approaching 2. We want to approach 4, f is approaching 2. So for this graph, the limit of f of x will always be 2. We can extend this to no matter what the constant is. So let's take a quick look. We want to manipulate the plot of the constant function c. We'll do a domain of minus 5 to 5. Just make the curve black. Let's keep the plot range of the constant minus 5 to 5 as well. And we'll let the constant c range from minus 5 to 5, just to see what we get. And if we just go ahead and let this play, we can see that no matter what the value of c is, the limit of that c will always just be c. Let's randomly pause somewhere. Let's say right here. Right, no matter what we're approaching, this limit will always be this line. In this case, the value 3.95699. So we can generalize that the limit as x approaches a of c will always be c, where c is just some real number. We now go ahead and look at the actual limit laws. Oops. Laws. So for all of these, we're going to say let f of x and g of x be defined for all x not equal to a over some interval containing a. Assume that both the limit as x approaches a of f of x and the limit as x approaches a of g of x exist, and we'll say that the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m. Right? And L and M are just real numbers. Furthermore, we're going to say let C be a constant. Our first law, the limit as x approaches a of f of x plus or minus g of x is equal to L plus or minus m. So what this says is that if you're taking the limit of a sum or difference of functions, then the result is just the sum or difference of the individual limits. Our second law, the limit as x approaches a of c times f of x winds up just being c times L. So if we take the limit of a constant multiple of a function, the result is just the constant multiple of the limit of that function. Third law, the limit as x approaches a of f of x times g of x is just L times m. So this says that if you take the limit of a product of functions, the result is just the product of the individual limits. Number 4, the limit as x approaches a f of x of a g of x will just be L over m as long as m is not equal to 0. So this says if you take the limit of a quotient of functions, the result is just the quotient of the individual limits as long as the bottom function, the denominator function, is not approaching 0. Fifth, the limit as x approaches a of f of x raised to the nth power is equal to L to the n for every integer n. This says if you take the limit of a function raised to an integer power, the result is just the limit of that function raised to that integer power. And finally, number 6, the limit as x approaches a of the nth root of f of x is equal to the nth root of L, where L has to be greater than or equal to 0 if n is even. Right, so this says if you're taking the limit of a root of f of x, a radical f of x, it is just the radical of that limit. Now, since we can't have negatives under even indexed radicals in the real plane, right? Remember, in complex, if you take, for instance, square root of a negative number, you wind up with a complex number. But we're only dealing with the real plane here, so if the radical is even indexed, the limit must be greater than or equal to 0. These are the 6 limit laws. Now note that these 6 laws are also valid if the limit happens to be one-sided. We will now look at several examples. So first, let's go ahead and evaluate the limit as x approaches 2 of 2x squared minus 3x plus 1 all over x cubed plus 4. Now, in the last video in this series, we did a table of values. Here, we're going to actually use the limit laws. Now, the first law that we see here would be a quotient. And that was law, should be number 4. Go away, keyboard. Law number 4. So I'm just going to write over here, this is by law 4. Limit as x approaches 2 of 2x squared minus 3x plus 1 divided by the limit as x approaches 2 of x cubed plus 4. And remember, this is only going to be valid as long as this limit is not 0. And we can rest fairly confidently that this will not be 0. Now, the numerator is sum difference, limit of a sum or difference, and so is the denominator. So that is the first limit law. What I'm going to do is I'm actually going to move it down to a new line. So by limit law number 1, I can write the numerator that way. And then the denominator we can write this way. Right, so now this limit here is a constant multiple. This limit here, constant multiple. Nothing else. So we can use the constant multiple law, which is law number 2, to rewrite the numerator. Now if we look, this limit here is a power. This limit here is also a power. So we can use the power rule, which is law number 5. This will allow us to rewrite it this way. Now we're finally in a position to go ahead and try and evaluate this, because notice now we're strictly in terms of limits of x's or constants. And we can use these two basic limits to evaluate them. So these are just now by the basic limits. We just plug in 2 for x, and the constants will stay the same. So we're going to have 8 minus 6 plus 1 all over 8 plus 4. So that's 3 over 12, which will simplify down to a quarter. Now, an interesting observation to make. If, at this step right here, we were just to plug in 2 for x, then we would also get 3 over 12, or 1/4. So, it appears that we can just plug in a for x, and that would give us our limit. In other words, this is just an observation. It appears that the limit as x approaches a of P of x equals P of a, where P of x is a polynomial, and the limit as x approaches a of P of x over Q of x is P of a over Q of a, where Q of a, Q of a is not 0, and both P of x, Q of x are polynomials. And in fact, this idea also extends to if we have roots as well. So that means we don't have to keep going through all of this. Right? So this observation is easily provable using those limit laws. We will not go over that proof in this video. However, we are going to use this observation now to evaluate 3 more limits. So first, let's look at the limit as x approaches 3 of 2x squared minus 3x plus 1 all over 5x plus 4. So we're just going to plug in x equals 3. We have 2 times 3 squared minus 3 times 3 plus 1 over 5 times 3 plus 4. All right, we'll have then 18 minus 9 plus 1 over 15 plus 4, which is 10 over 19. And so there's our limit. Now let's look at the limit as x approaches negative 4 over 5 from the left of the same function. So if we plug in negative 4/5, we get 2 as negative 4/5 squared. So that observation also works for one-side limits. This would leave us with 32 over 25 plus 12 over 5 plus 1 all over negative 4 plus 4. Now we have a problem, because this here winds up being 0. And we cannot divide by 0. However, if we use some intuitiveness, if the numerator remains constant and the denominator is getting smaller and smaller to 0, well, as the denominator gets smaller, the overall fraction would increase. So it would appear that this is going to be an infinite limit, right? It's a vertical asymptote. We could create a table to determine whether it's approaching positive or negative infinity, or we can do a little investigation. Now, the numerator is always going to be positive. Right? We have a positive number plus a positive, that's positive. So whether this fraction is positive or negative will solely depend on the sign of the denominator. Well, if we're approaching negative 4/5 from the left, that means we're taking values smaller than negative 4/5. Well, negative 1 is smaller. So if instead we plug in negative 1 here, this would become negative 5 plus 4, which is negative. So this limit is negative infinity. If we take the same limit now, but instead approach from the right. We're going to have the same situation. So no need to reinvent the wheel. I can just recopy this. But now we're approaching from the right, so we're taking values that are larger than negative 4/5. Well, 0 would be larger. If we plug in 0 here in the denominator, we'd have positive 4. Denominator is positive, numerator is positive. And so this limit is positive infinity. All right, that concludes this video on the limit laws. In the next video, we will look at what happens if, when we plug in the value that x is approaching, like we've been doing here, and we get something like 0 over 0, known as an indeterminate form. We'll look at ways to evaluate limits in those cases.